Hello, it's Keith here, and this is lesson 58 of the platform-specific series of my 650 assembly programming tutorials. We're looking at Mintile, my multi-platform minimal tile map. We're looking at the PC Engine version today. Now, of course, the PC Engine has a hardware tile map, so what we'll be doing is we'll be transferring the data from the software tile map configuration into the hardware tile map. But what we're going to have to do is we're going to have to transfer the tile data, the patterns, to the VRAM memory. Now, an interesting thing about the PC Engine is, despite being fairly advanced graphically for what most people would call an 8-bit system, it's 6502 is an 8-bit processor. They often called it 16-bit because its graphics chip was 16, but I'd say it's 8-bit. One thing that's surprising is that the tile map can't actually X-flip or Y-flip the tiles. So what we're going to have to do is we're actually going to have to X-flip the pattern data, because Mintile is designed to support horizontal flipping, because it was written originally for a Street Fighter party called Chibi Fighter, and that needed the characters to turn around. So we're going to have to do that in software, and that's what we're going to see today. So I think this will be interesting for you if you want to see about how to configure the PC Engine tile map. Even if you're not interested in Mintile, it'll give us a nice refresh on the tile map. Anyway, this is what we're creating today. You can see we've got two characters moving around the screen. These are simulated sprites using the tile map today. This version doesn't use hardware sprites. I'm writing a version called Max Tile, which will use hardware sprites on all systems. So that is a limitation of this example. Anyway, let's go over to our code and let's take a peek. Okay, so here is the example today. We are looking at PCE Mintile here. This is the example. Now, as I would say, we're not going to cover the general code, the stuff that hasn't really changed and I use generically in all cases. All of our screen setup and things are the same as always. Now, the first thing we've got here is this send tiles routine here. We've got define tiles combo. Now, this is a modified version of the defined tiles routine I've used in the past. We are specifying our source bitmap here. We're specifying the length in bytes here. And we're specifying the VRAM destination, memory address 1000 in hexadecimal here. Now, the VRAM on the PC Engine, all of the VRAM basically is kind of tiles. So part of the VRAM is going to be used for the actual tile map, the definition of which patterns to show to the screen. But the tile patterns themselves are also in that area. So when we're defining 1000 as our first tile pattern, the memory address 0, if we tried to use that, that would actually be used by our tile map, the grid of tiles that are being shown on the screen. And that is something that caught me out in the early days because I couldn't figure out how to get the patterns working, and it was because I was overwriting the tile map and the patterns were the same thing. Anyway, so we're going to start from tile number 256, which is at memory address 1000, and we're going to use define tiles combo. This is this new version of the function, so let's have a look at that. Okay, so what does define tiles combo do? Well, it basically defines the tiles twice. Now, we've got this define tiles routine which has been modified to allow a horizontal flip, but not a vertical flip at this stage. That's too advanced for this lesson. So it will allow us to horizontally flip the data if required, and the way we define it is by setting IYL at this point to 1 or 0, 1 being flipped. Now, we're loading that into the accumulator here, and we're just backing up the registers that would be changed so that when we run this both times, the byte count and the source bytes will be the same. Now, the destination RAM, we're effectively adding 4000 to that, and that is the address that we're going to write our X-flipped tiles to. So we're defining two sets of the pattern data, once normal, once X-flipped, memory address 4000 onwards from the original set. So if we were uploading multiple sets, they would all be offset in that fashion. Okay, so when it actually comes to transferring the data, basically what we've got here is we are defining the VRAM destination with the memory mapped registers 102 and 103. These are the VDP ports for defining the destination memory address, and so we're writing the address there. And then what we're doing here with ST0#2 is we are selecting the data register, and so here we were selecting the address register, selecting that we want to select a destination, and here we're selecting the data register, meaning we want to actually write data. And then we've got two commands here for do source pattern byte here, and we are basically transferring a pair of bytes with each sequence here. Now, the reason we're doing two each time is the PC Engine, the alignment of its memory, that works quite well. Now, we're doing two here because we need to write to those two ports. We're going to repeat for the value in BC. We actually loaded C into the X register here, and B is being decremented directly in the 0 page. We're decrementing X by 2 each time because we're writing 2 bytes each time. So this do source pattern byte is actually doing the job of doing the flip if we need it. So here we're checking IYL, and if IYL is 0 in the 0 page, then we're unflipped. So we're loading in a source byte here from the accumulator and incrementing the Y source here. But if it is flipped, we're loading in from the HL source here, and then we're flipping all of the bits. The data is of course in bit planes, so each line contains 1 bit of each of the 8 pixels, and there's 4 bit planes in total for 16 colors. So we're doing our 2 bytes here, storing that will load them in and flip them if required, and then we're storing them using the 2 registers, the 2 VDP registers there, and that is doing the transferring of the pattern data that is our graphics of our Chibico and our background here, and it's also handling the flip because we're running it there and again there. So that's defining our graphical data. Now that's actually the tile map. The Chibico mascot, the simulated sprite, there is actually a miniature tile map. You can see that just here. And the actual pattern tile data, the graphics if you will, where is that? Here it is. Here's the actual data. So those are the tiles for the background, and those are the tiles for the mascot, the Chibico mascot there. So that's what we're using. Now the Mintile routine, it's a multi-platform routine, and so it works in a common way on all systems. Now most of the code is multi-platform, and I have a separate tutorial for that. The Mintile series covers the multi-platform code. This does most of the generic work, and it only passes the final part of the drawing process to the platform specific code. And the way it does it is it breaks down an object, either an entire screen or a little sprite, into strips, and it tells the platform specific code to draw that strip, and the strips are drawn from left to right for each line, and it repeatedly calls that routine to draw whatever it is trying to do. So in the case of this system, all we need to do is basically read in the source tile numbers and then write the destination patterns that we want to show at that position in the tile map. So what we're doing first here is we're selecting the VRAM destination here by writing the HL VRAM destination. In the HL and the 0 page are the VRAM destination here, and we're writing those, and then we're selecting that we're going to write data using port 2 here. Okay, now what we're going to do next is we're going to load in from BCS, that's a 16-bit pair in the 0 page. BCS and HL are both 16-bit pairs, and so that is the tile map data, the source data that we saw before. It's just a grid of 1-byte numbers for the tile numbers we want to actually show. Now the way Mintile works is it supports just a single byte, so 0 to 255, but 0 has a special meaning. In the case of a sprite, this is a transparent area. You can see around Chibico's feet there, that is transparent. And in the case of the background is actually a cache of changes. So a 0 means that nothing's changed since last time. You see, Mintile is designed to work with just 1 screen buffer. Some systems really can't provide enough memory for more than 1 screen buffer, and so working within that limitation gave more flexibility for working on multiple systems. And so the tile cache is a cache of changes that need to be written to the screen, and a 0 in that cache means something that's not changed and nothing needs to be done. So when we read in our byte from the tile map here, if it's a 0, we're simply skipping all of the drawing routines and we're jumping down to here, and that's just going to skip over, moving to the next VRAM destination. Now if it's not 0, then we actually need to start processing this tile. The first thing we're doing is we're checking the tile clear flag. Now this is a flag in memory, and this defines whether we actually need to 0 the bytes after writing them. If we're working on the background tile map cache, then yes we do. If we're working on the sprites, no we don't. This would be done with self-modifying code on some systems, but we're running from ROM here, so that's not an option. So in the case we're zeroing it, we're transferring X to the accumulator and storing it here. Now X is 0 throughout this routine. We load it with 0 there. So we're transferring the X to the accumulator here and storing that in there. Now what we're going to do next is we're basically going to take the tile number, which we loaded in there and we backed up into Y. We're getting that back, and we're going to add the DE base. Now DE in the 0 page is the offset to the tile number that represents the first in this tile map. Now the background can use a different set of 256 tiles to the Chibico, for example. So we actually have a range of 256 tiles per object, so 1 set for the background and 1 set for each sprite potentially. So that gets around some of the limitations of a single byte per tile. So DS and ES, the DES pairs, I refer to them sometimes, in the 0 page are being added to the byte that was loaded in from the tile map and selected as and written to the tile map as the byte to be shown at this position within the tile map. This is writing to VRAM now, so this is actually making the tile visible. We're then incrementing the HL VRAM destination, and we're just then going to basically increment the source tile map address, and we're just going to repeat until we've done the entire width of the tile map, which is defined by 0 page entry IYL. Now, if you're wondering what these BCS and IYL and things, what these letters mean, they don't really mean anything. I'm mimicking the Z80 registers so that I can port the code between different systems, and IYL is just an 8-bit value on its own, and BCS is just a 16-bit combined value. The S stands for shadow. That would be a shadow register on the Z80. So really all you need to know is that these are values in the 0 page. The purpose of them is defined here. For this subroutine, they will have different purposes in different parts of the code. It's just a convenience for porting to many systems. Now, when we come across an empty tile, we increment the HL destination, and then we select manually the new HL destination so that the drawing position is in the correct position for the next draw. The do strip reverse routine basically reads in the tile map backwards and flips each of the tile patterns. Now, on a bitmap system, it would calculate the flip. On this system, though, all it needs to do is use the alternate set of tiles. So before we were adding DES to the selected tile number. We're doing the same here, but this time we're adding 4, effectively adding 400 to the selected tile number, and that is the equivalent of selecting VRAM address offset 4000 there. So that is the effect of doing that there. So that's what we've done, and that is selecting the second set of tiles, which are the XFlip versions, and that's how we're able to make our character XFlip. So there's our normal character, there's our XFlip character, so that's how we've done that. Now, there are some bits that are unused in the destination. Basically, the first 12 bits of the 16-bit value that's written here is the tile number, and the remaining 4 bits are the palette. Unfortunately, there is no hardware XFlip or YFlip or anything like that on the PC Engine, so we can't use it because it doesn't exist. Anyway, that's all there is for today. As I say, we'll be looking at a far more advanced version of this called Maxtile, which has other features, and I'm hoping to get hardware sprites working on this system. That's my goal anyway. So if you want to see that kind of thing, please stick around for that. Like and subscribe, all that kind of thing. And of course, go to my website and download the source code and have a go with it. If you want to see other stuff on tilemaps, I've got some stuff in the simple series about using the tilemap to show simple bitmaps and move objects around the screen using the tilemap. So maybe those would be more convenient if this one's a little bit complex. As I say, Mintile is all about making lots of different systems with different capabilities do the same thing as an end result, so might be too complex for you. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.